I want to go through how to solve all the parts of the 2022 AP Calculus AB FRQ 2, which is about finding the area between two curves and then finding volume and some related rates at the end. So I'll go ahead and read the question, which is, let f and g be functions defined by f of x equals the natural log of x plus 3 and g of x equals x to the fourth plus 2x cubed. The graphs of f and g are shown in the figure above and intersect at x equals -2 and x equals b, where b is greater than 0. So I went ahead and wrote and drew out a visual of these graphs and also the information. So f of x is our graph on the top, g of x is our lower curve, and I went ahead and solved for b already, but this isn't given to you, so this will be something that if you were taking these FRQs, you would have to do on your own on your calculator. But luckily, it's not too difficult, and I have a video on how to do that on your calculator if you're not sure. So let's dive into part A. Part A says to find the area enclosed by the graphs f and g. Well, this should be pretty easy for us now. We can say that area it's just the integral from -2 to b. This is definitely a time when you would want to integrate across your x-axis just based on the situation. And so that's why I'm using -2 to b. And then it's just our upper graph minus our lower. So we're given f of x minus g of x with respect to x, or across x. And this equals 3.603. And so that is the area between our graphs. So we're already done with part A. Now moving on to part B. Part B says that for -2 is less than x is less than b, let h of x be the vertical distance between the graphs of f and g. Is h increasing or decreasing at x equals -1/2? And then give a reason for our answer. Well, we know that the vertical distance between our graphs, well, we just figured that out. It's the top graph minus the lower graph, because if you think about it, you have to go up to your top graph, which is f of x, and then subtract this little portion from your lower graph. And this even works in this region where you would have a positive top graph, so whatever y value this is, and then you would subtract this negative part, and so your total length would be longer because it's minus a negative for our lower graph, which is a positive. So that's the justification for doing this. So we know that h of x, then, it says is the vertical distance between our graphs. So it's our upper graph, f of x, minus our lower graph, g of x. And we want to know if it is increasing or decreasing at x equals -1/2. Well, just from looking at our graph, we can probably infer that it'll be decreasing, because if, say, right here is like -1, then here's about -1/2, and you can see that the distance between these this upper and lower curve is getting smaller, but we do have to prove that mathematically, so let's do that. So to find if a function is increasing or decreasing, you take the derivative to find its slope. And so this is a very easy derivative because it's just h prime of x equals f prime of x minus g prime of x. I know this almost seems like too good to be true, but this is just your derivative. It is that easy. And so then if we solve for h prime of -1/2, we do in fact get -0.599, which is less than 0. So it is decreasing. And on the AP test, you do have to write a full complete sentence, but I'm just using some shorthand for the sake of the video. All right, so that's part B. For part C, So part C says that the region enclosed by the graphs of f and g is the base of a solid. cross sections of the solid taken perpendicular to the x-axis are squares. Find the volume of the solid. So I'm just going to write out that these are squares, just to make sure I remember that. And so we know that the volume is, well, it says it's perpendicular to the x-axis, so my limits of integration are going to be my points of intersection, the x values, which are -2 and b. So therefore, this is the integral from -2 to b. And then if they're squares, that makes it super easy because it's just the distance between these two curves squared. If you imagine a square being built up along here, all its side lengths would be the same. So I'm going to say that this is my upper graph, f of x minus lower g of x squared across x. And this equals 5.340. That is the volume of this solid. Okay, now for part D. Part D says a vertical line in the xy plane travels from left to right along the base of the solid described in part C. The vertical line is moving at a constant rate of 7 units per second. So therefore I can say that my change in x with respect to time equals 7 units per second. Find the rate of change of the area of the cross sections above the vertical line with respect to time when the vertical line is at position x equals -1/2. Okay, so let's break down what they said. What we're solving for is for our change in area with respect to time. Something that's important to note is that I've been doing everything up to this point with respect to x. Like all my integrals have been dx, and my derivative in part B, I was deriving with respect to x. But now we need to find our change in area with respect to time. And so that's what we're solving for. And we know that at this point, our x value will equal -1/2. So I want to show, using some software, what this actually looks like. Okay, so what I have here shown on my screen is I put in my two graphs, f of x and g of x, which you can see here in the upper right corner. So my top graph is natural log x plus 3. My lower curve is x to the 4th plus 2x cubed. And you can see that this software generated two visuals of this graph. So now I have selected square already because that's the type of solid that they want us to generate. But what part D was saying was that there's some line traveling along the base of this shape at a rate of 7 units per second. So I just want to show you what this would look like. So if you look on the left side of the screen, as I slide this along, you can see that a line is generated that's moving across the base of this solid. And they're telling us that this happens at a rate of 7 units per second, which isn't really a real time value. It's just a placeholder, basically. But then if you look on the right, you can see a square being built up as this line moving along our base travels. And so hopefully this gives you a better idea of what they're talking about in part D, because what they're asking us is at when x equals -1/2, so that's about here, we want to know what the rate of change of this square on the right, which maybe if I turn the graph, it's a bit easier to see, what the rate of change of the area of this square being built up from the base is. Hopefully that software gave you a better idea of what we should be visualizing for part D, but now let's actually get into solving the problem. So I'm just going to write down that my area is, well, we actually found the area in part C, and the area between these curves is our integrand, which is f of x minus g of x squared. Because when you think about it, what we were doing in part C is we were taking the sum of all these infinitely thin, kind of super duper flat, like two-dimensional squares, and we were doing the sum of all those infinitely many thin squares from -2 to b. And so therefore my area is just f of x minus g of x squared. But I want to solve for the change in area with respect to time. So I can say, well, if I did the derivative of my area, I would be getting our change in area with respect to x. But now I want to convert this somehow to be my change in area with respect to time. Well, this actually is pretty simple because we know that our change in area with respect to x times our change in x with respect to time, if we rearrange this, well, we can simplify this because we'll get dx over dx, which is just equal 1 because it's same over same, and you get our change in area with respect to time. So now let's actually do this. So I'm not going to write out the actual derivative for area. I'm just going to say dA over dx times 7, which is our, as they told us in the problem, that's our change in x with respect to time. Well, if you doing the derivative on your calculator, you would get that this is equal to negative 9.271. And it's important to put units per second. And so that is the rate of change of the area of this cross section at x equals -1/2. And so again, if you're not sure how to find a derivative or a rate of change on your calculator, I do have a video on that, so definitely check that out. And it's important to note just real quickly that it's just 7. 7 is a constant rate of change. Just no matter where it is, it's like kind of moving this line along the base at a rate of 7 units per second. So that's why it's just times 7, and we don't have to factor in this x equals -1/2 to that part of the problem because it'll be the same no matter where it is along this base. So I hope this video was helpful. I hope that the software helped you to get a better idea of what this would actually look like, and I will see you in my next video.